Okay, so if there are no questions, I'll begin. Okay. So far we have studied the motion in Schwarzschild geometry, but only for trajectories which stay outside the rho equal to 2gm surface, right? So today we are going to try to analyze what happens when you go beyond rho equal to 2gm, right? When you try to go inside, okay? And because at rho equal to 2gm there is a singularity, right? In order to study what happens when you go beyond, you have to first find a coordinate system in which the metric is non-singular, yeah, right? So that's what we will start with. Okay. So physics at rho less than 2gm, this is what we want to study. So find first non-singular coordinate, find coordinate system in which the metric is non-singular. Okay, so I'm going to first write down the coordinate system that we're going to use. Okay, so let me write the original metric. Okay. So theta phi we keep as it is, okay, but t and r we change to t prime r prime. Okay, and let me give the definition. So these are called the Kruskal-Zekeres coordinates. So this will be given in some slightly implicit form. So this is given in a slightly implicit form, in the sense that you are supposed to suppose you are to find r prime and t prime in terms of rho and t. Okay, this t is just a constant. Let me write t is just a constant, arbitrary constant. That if we want to find r prime and t prime in terms of t and rho, we can solve these equations, and we'll discuss later how to solve this. If we want, on the other hand, rho and t in terms of r prime and t prime, right, you have to solve these equations back. So this one, for example, will give you t equal to 2mg times tan I hyperbolic inverse times this. For this one, we cannot write a closed form solution. Nevertheless, we'll see that this is a monotone increasing function of rho in the appropriate range between rho equal to 0 and infinity, right? And so because it's a monotone increasing function, we can always solve for rho in terms of r prime and t prime. Okay, even though we don't have an explicit analytic expression for rho in terms of r prime and t prime. So this coordinate transformation is a well-defined coordinate transformation that I have written. Is this point clear? Oh, how? Well, I'm not told you how, right? I'm just saying that let's just introduce new coordinates r prime and t prime, which are related to the original coordinates rho and t in this way, right? And what I'm saying is that this is written in a somewhat implicit form, because normally you would say that you should give r prime as a function of rho and t, and t prime as a function of rho and t. That can be done in principle by solving these equations, but I have not given this, right? And the reverse, rho and t in terms of r prime and t prime, right, is a little more complicated. This one you can easily solve. This is 2mg times tan hyperbolic inverse this. Okay. This one you cannot write an analytic solution for rho. Okay. But nevertheless, because this is a monotone increasing function, right, which again we will see, we can in principle write rho in terms of r prime. Why? Well, the point is that now, of course, one can try to give various justifications, right? When it was first found, it was just found by trial and error, right? I mean, we didn't know beforehand that if we just look at the metric, right, there's a singularity, right? How do you know that there's a coordinate transformation that will remove the singularity, right? Okay, that people could figure out because you can calculate, for example, the Riemann square, right? Scalars, and you find that those scalars are all finite at rho equal to 2gm. Okay? But then to actually construct a coordinate transformation, right, you have to basically try to do by trial and error, right? You basically, okay, so essentially what you have to do is that you go close to rho equal to 2gm. Okay, so that the metric can be approximated, right? It looks like something, say, you can, if you define 1 minus 2gm over rho as, say, rho tilde, okay, then the metric here looks like something rho tilde dt squared. And this one near rho equal to 2gm will be essentially some constant times dr squared. Sorry, this is d rho square. D rho tilde square over rho tilde. Okay, this is only approximate near rho tilde equal to 0. Right? This you can easily check because you just have to. This is of course directly by definition rho tilde. Here you write rho in terms of rho tilde by using that, and then you expand whatever coefficient comes near rho tilde equal to 0, right? And you will find that it basically goes as 1 over rho tilde, and that comes because this is in the denominator. And then you can ask that given this, right, what can you do to make this non-singular? Okay. So the insight is that you can first make it look like the kind of singularity that we have at the origin of polar coordinates. Okay, so let me show that. So let's take, we'll define rho tilde as introduce a new variable, say w square. Okay, so then this becomes like minus w square dt square plus c times this becomes 4w square dw square over w square, right? Okay. So this is minus w square dt square plus some constant 4c dw square. Okay. Now imagine that you have a two-dimensional space, okay, and you are trying to describe it in the polar coordinates, right? A two-dimensional space in polar coordinates will be like dr square plus r square d theta square. So does it resemble this in some way? There's a minus sign, of course, right, which you have to worry about, right? But without the minus sign, you can see that there is one whose coefficient is finite. That looks like dr square, right? And then there's another one, right, whose coefficient goes as quadratic in this variable r, right? Here you know how to change coordinates. XY coordinate written in terms of r and theta will give you non-singular metric, right? Okay. So you follow that same intuition to try to find a coordinate transformation here. Right? So this way you can figure out what kind of coordinate transformation you should make near rho equal to 2gm. Okay. The full coordinate transformation is of course arbitrary, right? Because any other coordinate, right, which has the same feature near rho equal to 2gm will make the metric non-singular. Right? But this has, we'll see that this has some specific features that makes it useful. Are there questions? Right. So the essential idea is that near rho equal to 2 gm, where we are going to study the metric after a few change of coordinates looks like the kind of singularity that we will have at the origin of a two-dimensional space if you write it in the polar coordinates, right? And then you use the insight from these two-dimensional polar coordinates how to change coordinates from r theta to xy. Right? That change of coordinates is singular, okay? Because that's why in the r theta coordinate, right? You can see that theta theta component is 0. Right? The g theta theta is 0 because there's an r square sitting in front, right? At r equal to 0 is a sinus. So it's singular, the singular metric. But in the xy coordinate, of course, there's no singularity, right? It's just dx square plus di square. So that change of coordinates you generalize to remove the singularity from here. Yes, indeed. Yeah, so rho equal to 2 gm is not genuine singularity, right? Because in this, okay, I have not written down the metric. I'm going to write down the metric in this coordinate system, right? And it will not be genuine singularity. Yes.
How did you write that d rho theta squared? I mean, just d rho squared, right? D squared. Right, d rho theta, shouldn't we get some other factors also?
Yeah, but we are expanding around rho tilde, rho equal to 2 gm, which is rho tilde equal to 0, right? Okay, so yeah. So we are basically focusing near rho tilde equal to 0. Okay, so all those factors we set to whatever it is, right? Except that here, of course, you don't want to set rho tilde equal to 0, right? And the essential point is that it goes as 1 over rho tilde, right? Near rho tilde equal to 0.
Because we can see that rho equal to is a coordinate singularity. So always take care of the fact that there will be a coordinate system that will go to rho equal to 0 and go to rho less than.
Yeah, so we'll see that in r prime t prime, right? It goes to rho equal to 2 gm.
Can be non-trivial also, right?
Yeah, it can be non-trivial. It's true, right? Till you find a change of coordinates, right? You wouldn't know if the metric is singular or not, right? So, in order for the metric to be non-singular, right, you should be able to go to that point, right? Because it should be a regular point in space-time, right? So you should be able to take a spaceship and go beyond that point. Okay, if that doesn't happen, then the metric is singular.
This fact is also kind of guaranteed since we can see that R's don't have the tensor, etc.
The point is, it is one way. If the Riemann tensor square is finite, right, that doesn't necessarily mean that there is no singularity. If the Riemann tensor square blows up, right, r mu rho sigma, if it becomes infinite, then clearly there is a singularity, right? But reverse is not always true. You know, there are singular spaces where all scalars constructed out of Riemann tensors are finite. Right? Nevertheless, you can show that it's impossible to find a coordinate transformation in which the space will be non-singular. Right? So it's one way that Riemann tensor square being singular, right, implies that the space is singular, space-time is singular, but the reverse is not true.
The singularities are also not removable singularities.
Exactly, yeah. So if you cannot find a coordinate system in which the metric is non-singular, right, then those are non-removable singularities. That even if the Riemann tensor all scalars vanish, all scalars are finite. Yeah, but it is possible. I mean, there are examples of spaces where this happens, and the proof is complicated, but it is possible to prove that those spaces are singular. Yeah. If you can show it blows up, it will suffice. But suppose it doesn't blow up, right? These spaces that I'm saying are the kind where nothing blows up, right? Well, not that nothing blows up, the curvature, the scalars don't blow up, right? Nevertheless, what you can show that if you take a spaceship and go in that jump into the point, right? That point, then the spaceship will basically be torn apart. Okay, which is called as infinite tidal force. Right? Even though all the scalars are finite. Okay, so the physical definition of a non-singular space-time, is that you should be able to take a spaceship and go through that point, right, without dying. Right? If that doesn't happen, then the space-time is singular. Not necessarily, right? There are, as I said, there are examples of space-times, right, which are actually singular, right, and they're accessible. You can go into that singular point, and you will find that you basically hit basically you feel infinite force, infinite tidal force. Right? I think you are thinking of the this cosmic censorship or something, right? Those are special kind of metrics. Right? I'm talking about now the example of a general space-time, right? Where cosmic censorship may not hold. I mean, you can actually reach singular points by riding a spaceship. Okay, so let me write down the metric just to. So this is actually straightforward exercise, but it's tedious algebraically. Okay, that once you make that change of variable, metric takes a form this is the capital. This is a arbitrary constant. Which is R prime? Yeah, this one. No, rho is not R prime. That's important. Okay, so this is written in a somewhat strange way, right? If you are writing the metric in the R prime P prime coordinate system, then everything should be written as R prime and P prime, right? But in this coordinate system, that is not possible analytically, right? So you have to think of this rho, right, that is appearing as implicitly a function of R prime and P prime by solving this equation. Okay, it's just that we cannot solve it and write an analytic expression for rho. Okay, but rho should be thought of implicitly as functions of R prime and P prime. Is this clear? I'm going to show this. Yeah, I'm going to show. I mean, I'm going to map out the space from rho T to R prime T prime, and then we'll see what happens. Yeah, we'll study all those, right? Whether the solution is unique or not.
As we said that this transformation is well defined and it is not isn't that enough to say rho can be greater?
Yes, that is enough to say. Yeah, I have not proven that it's monotonically increasing. Yeah, but once you accept that, then that is enough to say. So what we see from here is that at rho equal to 2gm, there is no singularity. Everything is perfectly finite, right? Nothing vanishes, nothing blows up. Okay, so rho equal to 2gm is a regular point. So rho equal to 2gm. Okay, if you look at this equation over here, okay, you will see that this corresponds to R prime square minus T prime square equal to 0. So this corresponds to r prime square minus t prime square equal to 0, okay, which is r prime equal to plus or minus t prime. Okay, so the rho equal to 2gm surface has gotten mapped to this. Rho equal to 0 is still a singular point. Because you can see that this diverges. And that in any case we know because Riemann square diverges at rho equal to 0. Okay, you can calculate even in the original coordinate system, and you can check the Riemann square diverges at rho equal to 0. So it's not surprising that rho equal to 0 singularity you have not to do. So what is the rho equal to 0 surface? Let's look at this. So rho equal to 0 corresponds to r prime square minus t prime square equal to minus t square. Okay, because at rho equal to 0 this is 1 and this just becomes minus t square. So in the r prime t prime space, right, let's plot this. So t prime this way and r prime this way. These describe hyperbola. So this is rho equal to 0. And these surfaces, the asymptotes to this hyperbola, these are rho equal to 2gm. How is rho equal to 0? Well, you can see the metric has still looks singular, right? But and the Riemann square calculated from this actually is 0, is infinite. Yeah, so rho equal to 0 being singular, that you already know, even from here. Right? You can calculate the Riemann square and you will find that this is divergent. Okay, any other question?
So all these scalars that we are talking about, these are all constructed from the Riemann tensor. Some contractions of the Riemann.
Yes.
So how do we know that just looking at the contractions of the Riemann tensor is sufficient to say that?
No, it's not sufficient. It's necessary. That finiteness of those quantities.
Is it lower than we are sure?
Exactly.
But let's say they all of them are finite.
Yeah.
But so my question is, this set of scalars exhausts the space of all the scalars?
Well, you can take all scalars, the derivatives of Riemann tensor square, anything that you want to construct. If any of them blows up, then you know that space is singular, space time is singular. But even if none of them blow up, right? Even then there are cases where the space time is singular. Arbitrary, yeah, any scalar that you can construct, Riemann tensor square, its derivatives, right? any kind of contraction that you can make, right? All of those could remain finite. Nevertheless, the space time is singular, right? And in order to see this, you just follow a geodesic, and you will find that an observer on the geodesic feels infinite tidal force, right? So everything will be just torn apart.
How will you know that tidal force?
Well, if you take two neighboring points, right, they feel the relative force between this 2 blows up, right? Okay, yeah, you have to do some calculation, but tidal force you are familiar with, right? That neighboring points, right? If they feel different forces in opposite direction, right? If they feel all the same force, then the whole thing will accelerate, right? But if the force between neighboring points, right, becomes infinitely different, then the 2 points will be pulled in different directions, right? That's the meaning of infinite tidal force, right? And that's what will happen. That if you take 2 geodesics, right, very close to each other, right, you will find that the neighboring points are just getting pulled apart by infinite force. Okay, how do you calculate, for example, tidal force in the Earth, right? Because of the moon. You take the derivative of the force effectively, right? Right? You have to do similar thing here, right? How much is the acceleration differ between 2 neighboring points, right? If that difference blows up, right? This is a difference. This is a difference in the acceleration. Divided by the distance between the 2 trajectories, and in the limit when the distance goes to 0. Right? This is roughly the tidal force, right? And this, if this blows up, that means no observer can actually cross that line, right? Even if the Riemann square is finite, even if all the scalars are finite. Right? So this is the kind of singularity we encountered. Not here. Here, of course, this is a genuine singularity, right? Here the Riemann square itself blows up. But there are examples of space times. In this condition, if the Riemann tensor square is 0, right, is infinite, then of course, I mean, you don't even have to do such calculations. Yeah, you can show that. Yeah. Yeah, you just calculate d2x mu d tau square, right? Is the neighboring geodesics, if that distance, if the separation, right, starts increasing by infinite amount, right? The rate of increase of the separation becomes infinite. Exactly. Yeah.
That will be equal to negative of that.
Exactly. Yeah.
That to sort of work, the acceleration itself will sort of work.
Yeah, but if the acceleration blows up, right, that by itself is not a good enough reason to declare that the space is singular, right? Because acceleration, if you are in the local inertial frame, right? It's this one. Basically, you have to calculate this. Pardon? Yeah, you can calculate it in terms of the tau, right? The proper time of the observer, right? In the proper time of the observer, you can see, right, if there are neighboring points, right, each of which are moving in their own proper time, right, the rate of which and at which the geodesic diverges, right, if any derivative of that becomes infinite, right, then you are in trouble, right? And that's what will happen in this other kind of space-time where Riemann tensor square is still finite, right, but these derivatives can become infinite. Right? So any derivative of this, right, if it becomes infinite, then that is a issue, right? Because neighboring points, right, are filling things by infinitely different amount. Yeah, that's the signature that the space-time is singular, right? And that is that in turn you can use it to argue that it is impossible to find a coordinate system in which the metric is regular. Because if you can find a coordinate system in which the metric is regular, then this will never happen, right? Because neighboring points, then all the gammas are finite, right? They will always remain finite, and the neighboring points will never diverge by infinite amount. But that discussion is not relevant for this case, right? Here, the Riemann square diverges, and so there is certainly genuine singularity at rho equal to 0. Are there other questions?
Initially, you had rho greater than 2gm part of it. We are allowing all rho.
No, no, not negative rho's, because this is rho again less than 0. You cannot cross this. Right? You see the rho greater than 0. Because it's monotonically increasing, right? Implies that r prime square minus t prime square is greater than minus t square. Okay, so that part of space time is this one, is this white region. Right? Here you cannot, this part of space time is not accessible because you just cannot cross this line, right? This is a singular line. So in r prime t prime coordinate system, this white region is the space time that is relevant. Yeah, because this line, these lines are rho equal to 2gm. Right? So these regions are rho less than 2gm regions. Is this clear? Oh, this one is rho less than 0. Yeah, so this is not a part of the space time. Right? So only the white region, the unshaded region, is part of space time. Right? This is where the singularity is. Right? So you cannot just cross. So this part of the space time doesn't exist. R prime square, yes, indeed.
Singularity r equals 0. That was like a point.
Yes.
But and the rho r equal to 2gm was like a surface. So here we see that rho equal to 0.
Yeah. Yeah, so that basically means that the intuition in the original coordinate system was wrong. That is a singular coordinate system, right? Right? This is more correct. At least in these regions, this is the correct coordinate system, right? Here, of course, it's singular anyway. Okay, but nevertheless, the fact that it's a line will have a non-trivial consequence that we'll be discussing. Yes, yes. I mean, what he was saying that in the original intuition, right? We had the idea that rho equal to 0 is just the center, right? The one point in space time. But in this coordinate system, it doesn't look like that. Exactly. Yeah. See, in Schwarzschild metric, in the original coordinate system, you cannot even go rho less than 2gm. Right? Because at rho equal to 2gm, you encounter a singularity. In this metric, you can go all the way to rho equal to 0, but not beyond that. Okay, so before we proceed, we have to first figure out whether the map is unique or not. Yeah. Oh, thank you. Yeah, this is like a surface, right? It extends, right? Yeah, but this is the correct coordinate system, right? Okay, we'll see. I mean, I think the intuition that we get from here, right? We'll see a genuine physical consequence of that. I think then it will become clear, right? The difference between a point and a line. Yeah.
We change the coordinate system, but then we can't see in the coordinate. Calculation in stuff in this coordinate system.
No, you can see. Why not? If you take a spaceship and go inside, right? You can certainly. This is the coordinate system which you have to use, right? We'll see that from outside you cannot see, right? That is also will come out from this coordinate system, but you can certainly take a spaceship and go inside.
Space wouldn't.
Yeah, what? Well, you don't see from outside, right? What you feel, our equations are showing from outside, and indeed it's not. It doesn't look like that. That should be clear from there. If you naively take rho less than 2 gm, right? Then you can say that time becomes space and space becomes time, right? Because the dt square coefficient becomes positive now, right? And d rho square coefficient becomes negative.
These are the light comfort.
Okay, we'll come to light cone coordinate. Just a minute. Yeah. So this t prime r prime is the light cone coordinate, right? But we'll define what it means. Okay. So first, let's try to check the uniqueness. So is this map 1-to-1? So the first thing we observe is that the left hand side, okay, this quantity t square times rho over 2 gm minus 1 times exponential rho over 2 gm is monotone increasing. Is monotonically increasing. From rho equal to 0 to rho equal to infinity. Okay, at rho equal to 0, its value is minus t square, and here it's infinite. So to prove this, we just have to calculate the derivative, right? dd rho of this. That's t square times 1 over 2 gm exponential rho over 2 gm, and then plus t square rho over 2 gm minus 1 yes.
The chart, the diagram that we have, take all of the r prime t prime or you also have a finite range of r.
As it stands, no. I mean, you have to take all of it. Because space-time just extends, right? You cannot just stop the space-time anywhere, right? Except at singularity. So as it stands, indeed, you have to take all of it.
R prime.
Yeah, r prime can be negative also. The r prime is just a coordinate, right? That's because I have called it r prime doesn't mean that it has to be positive, right? I mean, r prime is just something that I have defined. So as it stands, yes, all of it has to be included. Okay, but we'll see. We'll come back to this in a few minutes. Of this one, I want to prove that it's monotonically increasing, right? Okay, so I take the derivative of this with respect to rho, and what we find is that you see that this minus 1 cancels this one, right? So this term cancels this minus 1 term. Okay, and what you are left with is t squared times rho over 2 gm which is certainly positive. right? Between rho equal to 0 and infinity, it is positive. So this shows that given r prime t prime, okay, given r prime t prime in that range, in this range. So given r prime t prime, so this implies that given r prime t prime with r prime square minus t prime square larger than minus t square, there is a unique solution for rho between 0 and infinity. Okay, because it is this function is monotonically increasing between 0 and infinity. Right? So you cannot have two solutions. Given the once you have fixed the left hand side, there's a unique solution. Well, that will be the next part, right? First, let's try to do the other one way. Right? Given r prime t prime, the rho and t are uniquely defined. Similarly, tan hyperbolic t over 2mg. This is monotonically increasing from -1 to 1 as E increases from minus infinity to infinity. Okay, so this basically shows that T is also unique. So given r prime t prime, T is unique. Okay, so at least one way it is clear. It's unique. Given r prime t prime, that is unique rho and t. Is this clear? So now we are going to study the reverse. Given rho and t are r prime and t prime unique. These are different questions, right? X equal to y square, for example, right? Given a y, x is unique, but given x, y is not unique. Right? So you have to study both of these. So suppose we are given rho and t. So which means that the right hand sides are fixed. Right? Given rho and t, right hand sides are fixed. So right hand side fixed. Okay, so let's write the equation as r prime square minus t prime square as a and 2r prime t prime over r prime square plus t prime square as b, where b runs between -1 and 1, and A runs from minus t square to infinity. Is this clear? So A and B are given to us in this range, right? Because you have fixed rho and R, rho and T. And we are asking about the solutions for R prime and T prime. Okay. So this one you can solve. You just write this. So the second equation tells us that R prime square plus T prime square is 2 R prime T prime by B. So let's just add this up. Okay. So add this up. We get 2 R prime square as A plus 2 R prime T prime by B. So T prime is B over 2 R prime times 2 R prime square minus A. Okay, which I can write as B R prime minus okay. So this shows that given R prime, T prime is uniquely fixed. Right? So the only thing we have to now settle is whether R prime is uniquely fixed or not. If we can show that R prime is uniquely fixed, then T prime will also be uniquely fixed. Right? In terms of rho and T. Because A and B are given in terms of rho and T. So now we are going to substitute this in this equation. So we get R squared minus R prime square minus B square over 4 R prime square times the square of that. Sorry, I can write, I'll use this form. B square R prime square. And the square of this will have plus 2 AB square R prime by 2 R prime, and then minus A square B square over 4 R prime square equal to A. Is clear? Now I'm going to multiply this by 4 R prime square. So we get 4 R prime to the 4. Okay, 4 times four times 1 minus B square R prime to the 4. Right? This 1 minus B square I took from here. This one will be, this R prime cancels, right? This 2 also cancels. So plus A times B square minus 1 right? So this is a quadratic equation for r prime square. So you can solve it clearly, right? It will have two solutions. Okay, so you can of course write down the solution explicitly, but we don't need to do that. Okay. The product of the two solutions, what is the product of the two solutions? Basically minus a square b square over 4 times 1 minus b square, right? So minus a square b square over 4 times 1 minus b square. And because b takes value in the range minus 1 to 1, this is positive, right? 1 minus b square is positive. So this is negative. Okay. So there are two solutions. Okay. The product is negative. Right. That means one solution is positive, one is negative. Right. The negative solution is not useful because this is a solution for r prime square. Right. R prime, of course, is a real variable. Right. So only the positive solution is important. Right. So that means r prime square is the unique positive solution of this. But this means that r prime has two solutions, right? This implies that r prime is plus or minus some positive number. Okay, there are two solutions for r prime which differ by a sign. And now if you go back to t prime expression, okay, so t prime is br prime minus ab over 2r prime. Okay. So if r prime changes sign, then t prime also changes sign. Is this clear? So that if r prime t prime is a solution, so if r prime t prime is a solution, minus r prime minus t prime is also a solution. Yes, we could, but we couldn't have said that these are the only two. Right, indeed. I mean, we can say that if r prime t prime solves it, right, then minus r prime minus t prime obviously also solves because the left hand side remains the same. Right, so twofold ambiguity you could also already guess from there. Right, but to show that that's the only ambiguity, right, you have to do some work. Yes. Which is okay because rho and t are not good coordinate system anyway, right?
Outside.
Yes. So outside you can declare that what is outside. Let me come back to that now. Okay. Up to this point it's clear, right? we are getting two solutions for r prime p prime, right? Which are just reflection around the origin. Yeah. So if you look at this diagram, right? Rho outside is rho larger than 2 gm, right? So in this diagram, that corresponds to rho larger than 2 gm. Rho larger than 2 gm corresponds to r prime square minus t prime square positive. Okay. That is these two regions. This region is r prime square minus t prime square positive, and this region, right, just a reflection of this, is also r prime square minus t prime square positive, right? So this is the region rho larger than 2 gm, and this is also the region rho larger than 2 gm. These two regions are disconnected, right? There is no overlap, right? Which means that you have a choice of declaring, okay, the original Schwarzschild metric, right? The rho larger than 2 gm region that you are seeing, either as this part or that as that part, right? We will declare that this is the part that we are seeing earlier, rho larger than 2 gm. Is clear? So a far away observer is somewhere here. But what we are seeing from here is that once you extend this matrix, right, using the non-singular coordinate system, another universe opens up. This part has no connection to this part, right? But nevertheless, right, once you decide that you have to use a coordinate system in which the metric is non-singular, right, you automatically open up another universe, right, another asymptotic region. Yeah, physically they are not equivalent. They are two different universes, right? You may be doing some experiment there, right? This may be completely empty. Okay. But it's just that if you try to take the Schwarzschild metric and extend it, right? You say that okay, you just see how the solution does, right? Because Einstein's equation tells us what the solution should do, right? You have no choice. If you try to extend the solution, right, using non-singular coordinate system, you automatically see this other part of space-time. In some sense, yes, right? We will see in more detail in what sense is disconnected. It's not completely disconnected, but yeah, I mean, for all practical purposes, it's disconnected. We'll study this in more detail. Yeah. I mean, you have to make a choice, right? Those will be equivalent, right? But you have to make a decision, right? Whether if you are saying that you are seeing a Schwarzschild geometry, right? You are sitting somewhere outside the horizon, right? This rho equal to 2 gm. Then you decide whether in the r prime p prime coordinate system you are here or there. Yeah, laws of physics are same everywhere, right? Once you go to local inertial frame, yeah, it looks the same. I mean, you are saying by laws of physics, you mean the metric here looks the same as the metric there. Yes, indeed. No, we have not ignored anything. This is the exact solution. No, it cannot. I mean, we will see that. Right? Theta phi doesn't help. But you see, what we mean by connecting these two also is not completely clear right now, right? The geometry is certainly smooth, right? There's nothing going on anywhere. So if you are willing to draw a space-like surface, right, you can certainly connect the two regions. Yeah, we'll study the time like not even geodesics, time like curves, and then we'll see what happens there. Right now, all you are saying is that there are two disconnected regions where it looks like you can choose any one of them as your asymptotic space-time and work with this, but you cannot avoid the other region. Okay, at least at the level of the solutions that you have studied.
So we saw that the exterior of the Schwarzschild coordinate system solution that maps to this right hand side or the left?
Yes.
Right. Right. But somehow when we go to this new coordinate system, we see there's actually we can work with a bigger space.
Not that you can, we have to, right?
How do you know that there is nothing much bigger than this which embeds this thing in?
Yeah, so that you can show it. This is a maximally extended Schwarzschild space-time. We cannot extend it any further.
How do you see that?
Because in this coordinate system, I mean, you can extend it only if you find the breakdown of coordinate system, right? Here it's totally finite, right? In the R prime T prime coordinate system, the only things are the singularity, right? If you encounter another singularity, then indeed you have to see if you can find a coordinate change, and that will extend it further. Yeah, so there are examples like charged black hole solutions have this property that you can extend it infinitely, right? Because you keep encountering singularities.
Is it always true that if you have a singular space, and is it always true that there is some maximal extent?
Well, it's not smooth. It is still singular. The coordinate singularity. Yeah, if you have coordinate singularities, then by definition, there is a coordinate transformation that extends it, right? And you keep doing it. Okay, now, fortunately, in physical space-time, we don't have this situation. Okay, so let me now explain the actual physics behind these kinds of geometries. Okay, how do you actually create these kinds of geometries in nature? So typically, you can see that we have made an idealized approximation, right, to describe the solution, namely that we have said that there is a point mass, right, and there is nothing outside, right? We have solved basically Einstein's equation in absence of matter, right? Which is a good approximation of in many cases, right? For example, the sun also we can describe as a point particle, right, in Newtonian gravity. But we know that in actual practice, when you go into the sun, then inside the sun, the formula for the gravitational potential that we write is not valid anymore, right? Because there's a matter distribution inside the sun. Okay. So similarly, okay, here what we are actually trying to represent is the metric around some stars. Okay, as long as the radius of the star, okay, is larger than 2gm, then of course this singularity itself doesn't exist, that apparent singularity. Rho equal to 2gm, the metric is not valid. But you can imagine a star whose radius is less than 2gm. This typically happens that if you have heavy enough stars, okay, then even if you start with a radius which is larger than 2gm, okay, it basically starts collapsing under its own gravitational pull. Okay, and eventually its radius becomes less than 2gm, right? That's the way these kinds of objects are formed, right? So the horizon is not a fictitious quantity. It does form because the star under collapse can become of size less than 2gm. Nevertheless, okay, the full geometry we have to ask if the full geometry can form, right, in such cases. And what you find that if we follow the collapse of a star, let me draw this r prime p prime plane again. If you follow in this r prime p prime plane, how a collapsing star looks like, right? The surface of a collapsing star. Okay, we assume spherical symmetric, so that in the theta phi space it extends everywhere, right? But in the radial and time direction, we can ask how does it collapse, right? How does the surface moves? And what you find that the typical trajectory is something like this. Okay, so this is the surface of a collapsing star. Which means that outside this region, we can trust the solution that we have written, right? Because outside this, it's just a point particle. But inside this, we cannot trust it because there's a matter distribution, right? So the solution is trustable. So in this region, the solution is trustable. Okay, you can see that as the star collapses at some point, its surface goes below the horizon, right? Below the rho equal to 2 gm. So indeed, this is part of the region that we can observe. That is a part of the horizon, right? That is certainly there as part of space time, but this part doesn't exist. This is a rho equal to 0. This is a rho equal to 0 surface. So the surface of the star will eventually collapse into the singularity. Okay, so the singularity is real because this part of the space-time that you can access, that is real, right? Even a collapsing star will give rise to the singularity, and it will also give rise to the horizon, rho equal to 2 gm surface. Okay? It's just that the other part of the universe we don't expect to exist in physical situation. Okay, when these black holes are formed out of collapsing stars. Yeah, so that's why I've cut it out. Yeah, that's why I've cut it out, right? All we can say that outside this, we can trust this part of the geometry. Right? In the interior, the solution is different. Okay. Yeah, the whole thing. Anything beyond this, we cannot trust. Right? Because this is the surface of the collapsing star. Right? Once you cross the surface, then there's a mass distribution. Right? And you have to resolve the equation. Yeah, so the new universe was on the left hand side. Right? So if you actually have a physically collapsing star, right, you don't have that part that contains a new universe. Oh, this you draw by writing the surface of a geodesic. You plot a geodesic in the radial variable, right? And this is one of geodesics that you can form. Of course, I mean you can draw it in many different places, right? Depending on when the star has actually collapsed. Yeah, but it doesn't happen. I mean, you can follow the geodesic and you find that this is the way it happens, right? It starts from forming and then it collapses. So you don't expose this part at all. It doesn't have to be geodesic. You can take any time-like curve. The surface of the star will have to follow some time-like curve, right? Okay, the general structure will not change, right? The actual shape may change, right? But the fact that it actually collapses, forms the horizon, right, that is still valid. Is this clear? Okay. So this is you should keep in mind that the geometry that you are studying, only this part is physically relevant. Okay? But we'll be working with the full geometry, right? Because once you understand the full geometry, of course, you can easily cut off part of it if you want. Okay? But let's try to understand the full geometry and see what it gives. Because the full geometry is still a valid solution to Einstein's equation. Right? It's just that it may not form in actual collapse of stars. Right? But there's nothing wrong with the solution itself. Okay, so you can study if you have a space-time like this, what is the physics? Yes.
In this kind of physical situation, the mirror thing that you said is completely forbidden.
Forbidden meaning the solution itself doesn't remain the same, right? You have to resolve the equations taking into account the matter distribution. And typically you will not find the other side.
From the earlier discussion, what we saw is exactly the same metric on in the fourth mirror.
Exactly. But there you assume that there is no matter anywhere, right?
But here also the matter is not going to the other side. There is no matter. I was expecting.
Yeah, but the other side you got only by extending the left right hand side, right? If this part itself the solution starts getting modified, right? Then you cannot just continue that to other side, right? The other side may not even exist. See, the other side you got because you tried to continue the solution to the other side, right? And that assumes that there's no matter distribution.
How the symmetry? I thought there will be a similar allowed, like you draw a region in which the solution can be trusted. A similar region will exist on the other side also.
Well, if the other side has collapsed a star, right? But inside there may not be any connection. You see, because we got the other side by starting from one side, rho larger than 2 gm, and then he said we want to continue the solution and see what we get. Right? If at some point, right, the equations themselves start differing, right, you can still try to continue, but there's no reason why you should get the other side. Right? So for a collapsing star, if you just solve, you have to start always from the side that you are familiar with, right? Then just continue. And you have to continue as long as you can continue. Right? Here what I'm saying is that once you start having matter distribution, the equations themselves change. So you can try to continue, but you will not typically get the other side. Right? You are thinking that the whole thing already exists, and then you are collapsing a star, right? But the point is that the whole thing exists because of the collapse of the star, right? At least the standard black holes that you are familiar with, right? What you see, for example, at the center of the galaxy and so on. Okay, so let's go back to this geometry and see what it represents. I'll keep this diagram maybe. Maybe I shouldn't have erased the metric. Let me write it again. Okay. Now, a physical trajectory must be time-like or light-like. right? Doesn't matter if it's geodesic or not. Right? Any physical trajectory must have either time-like or light-like trajectory, which means that ds square must be negative or 0. Now, if you look at this metric, you can see that the only place where there's a minus sign is here, right? So if ds square has to be negative, this means that dt prime square must be larger than dr prime square, larger than or equal to. It's not sufficient because you may get things from d theta and d phi, right? But it's certainly necessary that dt prime square has to be larger than dr prime square. Okay. I can also write this as saying that dt prime dr prime must be larger than or equal to 1. In the r prime t prime plane, this means that the tangent to the trajectory must make less than 45-degree angle with the particle. Is this clear? Right, and this is true not just for geodesics. Even if you have an engine, right, you cannot avoid this situation. Right, you have to have that any physical trajectory must make less than 45-degree angle with the particle. Okay. So this is what is called the light cone, and what it is saying is that the all trajectories, right, physical trajectories, must lie within this cone. Right, or well, not within this cone. From any point, right, any space-time point, you can draw a 45-degree angle cone, and if you start from here, right, you have to be confined within the 45-degree angle because you cannot go beyond 45 degrees. Is that clear? Now, there is one more thing we have to decide, right? Whenever you have a 45-degree angle line like this, we can either stay in this region or in this region, right? If you start from here, right, you can either go inside this or go inside that, right? But both possibilities are not allowed because there is a notion of future, right? So you have to decide what is future and what is past, right? If you start from here, you may receive signal from the past along this light cone, and you may go in the future in this direction. So the question is then, is increasing t prime the future or is decreasing t prime the future? Just because I have called it t prime doesn't mean it's time, right? It's some coordinate, right? We have to decide whether t prime increasing is future or whether t prime decreasing is future. Okay. So this you can decide by going far away, because far away the t and rho you have identified as the usual time and radial coordinates. Right? So there you know that increasing t is future. Right? That's my definition of time, because that t you have identified with asymptotically Minkowski space time. So you can ask far away, right, whether increasing t is future or whether decreasing t. Whether increasing t prime is future or decreasing t prime, and that you can figure out from this equation. Okay, let me write the relevant equation here. We had tan hyperbolic E over 2mg is 2r prime t prime over r prime plus t prime, r prime square plus t prime square. This I can write as 2 over r prime over t prime plus t prime over r prime. Right? I can write this. So if we define, say, x as t prime over r prime, I can write this as 2 times x plus 1 over x. And for rho larger than 2gm, we have r prime square is larger than t prime square, right? So this is less than 1. Outside the horizon, this is less than 1. Using that, one can show that this is increasing function of x. Okay, just take the derivative of this. It's 2x over 1 plus x square, right? You can take derivative and you can show that it is positive as long as x is less than 1. Which means that increasing t means increasing t prime. Right? Okay, so the future was increasing t. So future is increasing t prime. Okay, so at least in this region, future is increasing t prime. Okay, so which means that starting from any point, you can go within 45-degree angle, but only in the upward direction. And once you have decided that increasing t prime is future, then you cannot suddenly change the notion of future. Everywhere in this space time, future will be increasing t prime. Is this clear? Right? Imagine that in this region, we have said that future is increasing t prime. Right? In a neighboring point, we cannot suddenly declare that you can go backwards in time. Right? It better be the future is still increasing t prime. Right? In the neighboring point, the future should be increasing t prime, because this is a continuous space time. Once you have decided that increasing t prime is future, that will remain. Is this point clear? So now let's try to study what happens if you cross this line. If you cross this line, right, imagine that we are somewhere here. Then where can you go? You can go anywhere within 45-degree angle, right? If you have a sufficiently powerful engine, you can go anywhere within the 45-degree angle. But that cannot come out, first of all. Right? Future from here doesn't include the space outside. Okay, so if you have taken a spaceship and crossed the horizon, the rho equal to 2gm line, there is no way back. You also see that the only possible fate is that you will eventually hit the singularity. Right? So this is a sense in which rho equal to 0 is not a point. Right? A point you can always avoid. Right? Typically, if you have a point in space, right, and if you have a spaceship, you can always run your engine to avoid the point. Okay? This rho equal to 0 is not a point. It's the future. It's the end of time, right? For anybody who enters the horizon. Is that clear? Right? And this is not fictitious, because even in this diagram that will happen, right? Suppose the star has collapsed and formed the horizon, right? any observer that crosses the horizon, right, has no chance of coming back, because this part of the space time is the same as what we had there. Well, yeah, can go to the r prime less than 0 side, but not in this region, not outside. But if in the physical situation, of course, that region doesn't exist. You see, if you take this situation, right, then that region doesn't exist, but you still have this feature that once you cross the horizon, you cannot come back. You have to hit the singularity.
But you said that the surface of the collapsing star was tied like the.
Yes.
So how is, I mean, a timeline curve is going
Inside is not a problem. Here also you can start from here and you can go inside, right? So if you have a spaceship, even if you don't have a spaceship, right, you have no problem getting into the horizon, right? You just be stationary and the gravity will pull you towards the horizon, right? Geodesics enter the horizon. There are many geodesics enter the horizon. Right? Coming out is the problem. Right? Once you go in, then you cannot come out. Okay, so this is what is called the event horizon. So next time we'll try to map out in more detail the map between the RT coordinate system and the R prime T prime, because RT coordinate system, which is what an asymptotic observer will use, right? Or an rho T coordinate system. Asymptotic observer uses the rho T coordinates because that's a natural coordinate system. Okay. Now suppose you have thrown in a spaceship or something into the horizon, right? And you want to see what's happening to it. Right? How will it look from outside observer? Right? So for that, you'll have to map out the rho T coordinate system and the R prime T prime coordinate system properly. And then you will see what the various features you will see if you have actually thrown something into the horizon and observing it from outside. Okay, so what we described today is what will be the experience of the observer that is falling into the horizon. Other questions?
This is happening because we have to ensure that it makes any to the trade, we have to make the angle
Smaller than 45 degrees, right? Of course, if you can solve the equation and you can prove the same thing, right? But this advantage of this T prime R prime coordinate system that you don't have to solve anything, right? Just pictorially you can figure out, right? So that's why this kind of coordinate system, the light cone coordinate system, right, is useful, because whatever is the complicated function outside, right, what is important is that it has this minus dt square plus d prime dr square form, right? That's why this crucial coordinate system is very useful to understand what's going to happen to an observer, right? What are the limitations of an observer? Any other question?
In this kind of physical situations,
Yes.
you already mentioned, for example, if we have a spherical system, then we are solving the equation just outside, and then we are solving for the metric outside. So how are we sure that in this case also we have a singularity varying at rho equal to 0?
Because this part of the metric is identical, right? See, because outside this, right, the equation is the Einstein's equation in absence of matter, right? And all you have used is spherical symmetry. So this part of the metric you can trust, right? And that includes part of the rho equal to 0 surface.
Outside the star means the rho equal to 0 is not in the.
Or outside, yeah, it is. You are talking about space time, right? So you can see the outside the star, rho equal to 0 is in the domain. If you're thinking of a static situation where the star is fixed, right? But the star is collapsing, right? And you may imagine, okay, it will take infinite time to collapse, so you'll never cross the rho equal to 0, but it doesn't, right? Because the geodesics actually fall into rho equal to 0. So collapsing star actually gives rise to both the horizon and the singularity. Yes. Yes.
And you said that when sign changes, T prime goes to minus T prime. So you said two disconnected things. Ideally, you should take only the first quadrant.
Yeah. So once you have a physical collapsing star, you should only take this part. Yeah. Right? Not the first quadrant, you also have to include this part, a little bit inside the horizon, right? Anything that is outside the surface, you can trust. Oh, that part is not there. In a physical star, that part is not there. Right? So only this part is relevant. But the fact that there is an event horizon is still there in that picture, right? That once you go in, you cannot come out, and you just hit the singularity. But that part is not okay. Yeah, you can, but that part is not there, right? In collapsing star situation, that inverted cone is not there. But yeah, if you take this full geometry, right, then many things can happen, and we will study many of the, some of the unusual things that can happen. Right? One thing you can clearly see that from this side you can never send a signal there. Right? There's no communication because the light cones are always inside. But two observers from two sides can jump into the horizon and meet inside. Right? There's no problem with that because you can go like this. Right? Eventually both of them will fall into a singularity, but it can happen before that. Okay, so this has many unusual properties. Yeah, it was of significance, exactly. Yeah, it has some significance certainly. It's not singular. If you take a spaceship and go inside, right, you may feel nothing. If aim is sufficiently large, right, then the forces at the horizon may be so small that you will not even know that you are crossing a one-way barrier. Right? But eventually, once you cross, right, there's no way you can come back. Yeah, the point is people have tried, but there are general theorems which one can prove that spherical, even if it's not spherical symmetric, it doesn't help. Right? A collapsing star, unless there is a something that prevents the star from collapsing, right? There is this limit on the mass of the star. A star that is larger than certain mass will collapse into a black hole, right? Because it cannot be held by other nuclear forces. And then this is the fate. Right? You don't need spherical symmetry. Here of course you have used spherical symmetry to make things simpler, right? But it's not necessary that you have to have spherical symmetry. Right? The horizons can form nevertheless. See, not for this solution, because for this solution in the r prime t prime coordinate system, right? We have removed all the singularities that can be removed, right? Because r prime t prime coordinate system, the only singularities are at rho equal to 0, right? At r prime square minus t prime square equal to minus t square, and that we know is a genuine singularity, which you cannot remove. So for Schwarzschild solution, this is the maximally extended space-time. Right? It's not that you can create other universes, right? This is the maximum you can do. Any other question?
So one which is compatible with the geometry and the coordinate does not have similarity. There is no coordinate similarity. There can be physical similarity, but not coordinate.
Yeah, exactly. That's right. That if there is a coordinate singularity, then you don't know what happens beyond that, right? So in maximal singularity, the geodesics, for example, okay, will have to either continue forever or end in a singularity, right? That's in the rho t coordinate system. That's not the case, right? Because it's geodesic. If you take a spaceship and go in, right, rho equal to 2gm, you can certainly reach and cross. Right? It's just that cannot be described in the original coordinate system. Okay. So you have to keep going, right? All geodesics must be of that kind, right? It has to be extendable in the future and in the past, unless you hit singularities. And this space has that property, right? Any geodesic that you can draw, right, either goes for infinity, right, or it ends at the singularity.
That space time, that
Yes.
everything must be slower than this. How did this conclusion?
Because principle of equivalence, you can always go to a local inertial coordinate system, right? Where the flat space rules will be valid. Okay, so we'll continue tomorrow then. Oh, yeah, yesterday I just took it up.
Just like we I didn't go very I was not get to that.
Analytical coordinates of Young axes are very the person who may know where this is again studied it recently. Medium are also asking the perturbative quantities. Yeah. So that's the only one connection is trivial, but that usually the perturbative quantities are having same result as that. Well, these are the only two things, but depends on what the physical situation is, right? Because in this situation, yes, indeed, you on the other side, right? But otherwise, you cannot restrict to this or this. Well, that you are trying to multiply, and you have to know what will happen. If this is a geometry, then nothing will happen. You have to just follow it. But suppose somebody has decided this and somebody goes in some other object. And that object may hit. They don't have to be inverted with the alternate. One of the coordinate system is that. When the rotating coordinate system is that, right? You know that rotating coordinate system have to extend along zero equal to. Exactly. We know that beyond that you have to use another coordinate. Right? And there's no reason why you have to do one-to-one map between OT and that.
Is good.
Okay, but this cannot be extended anymore. Because in this coordinate system, you can see that the only singularity is that because you got a metric. Only singularities are at rho equal to 0. Right? Otherwise, this coordinate system has no singularity. There has no singularity, you have to use a new coordinate. It's good as well as
This is the name.
exactly. The coordinate system has no singularity, the metric doesn't come singular. And that coordinate system is good.
So I can say that this is
Yeah. That mathematically this is a good. Physically, as I said, if you have a collapsing star, then part of the space time gets up. Yeah. Exactly. But if you just think of it as a solution to answer, then this is a good. Yeah, because spherical symmetry, because of the spherical symmetry, because what we use for the outside vertices, right? The spherical symmetry and absence of that. Those are the only ingredients.
Matching of the solution. So
Yeah, yeah. What the solution is inside, right? But the point is solution outside you can trust. Inside of will be one more problem. Yeah, don't you want to go inside? Yeah, so if you, here of course you don't need crystal extension. But here if you want to go in, you need a crystal extension.
this is the crystal diagram.
This is a crystal diagram, part of the crystal diagram. Yeah, that is a crystal diagram. And this is when the star is collapsed. But outside you can trust the solution completely. Inside the solution will change. This is a collapsing star in the crystal diagram. No, I think that I'll before because it doesn't conflict with anything else.
Yeah, that's right.
Exactly. So I was thinking that wait for tetraeds, I think it's best to wait. Maybe they are saying that you have spinner or something. That's the conclusion.
Yeah, but I was also talking I think who are replying.
They don't know, yeah. So I don't know what to do about them. This is something okay, I'll not ask them an example. Okay, the tetrad is a technique. Okay, to motivate it, you need, I mean, gas spinners and
Yeah, I mean, no, but once you've introduced the tetrads to use them to do the spin
yeah.
and so on.
So they will not follow the rules.
And they also don't make a difference. The others do, because the others are doing focus electronics. So
That's
so
okay.
they know some difference.
But tetrad I think you can do without difference. Yes.
You can, but yeah.
Square of tetrad is 0.
Yeah, you can, but it becomes very messy when there are all these indices around. Definitely.
Yeah, I agree. But the point is, I think that's the price you have to pay.
If I have to accommodate those,
Yeah. So, I mean, do it in a way so that they follow the basic idea, but they may have to get a motivation why you are. Because without spinners, without react particles, I mean, metric is good enough. So, there's no need. But that in any case will postpone till the end of it. So, what I'm trying to do is that I'll do action principle and then action waves. After that, I'll move on to none of these will require me. In that sense, that's a separate topic. Yeah.
you will also plan to teach about
That's what I was planning. I mean, that is happening.
So
So I basically started as last two I did the bending of light.
there's the short story.
Yeah, I did that short. And in that short solution, I tested the bending of light. And then this character motion. This is another thing. And then I started with this stuff.
So this was I had a question actually. So part of the assignment, not quite part of the assignment. So when you decompose the reminder, you decompose it into some guided part plus some other which so then so now one usually defines this as the traces part and then one find the expression for sigma in terms of the. You can also show that it's confirming. So it's traceless as well as confirming. But there's some intuitive reason, some people reasons to think about why tracelessness implies. Usually in CFTs, the tracelessness of the energy moment of length.
Already I is a way to see this, right? I can't, but that's certainly very close